Hi everyone, welcome back to the Microsoft in 29 days self-paced course. So I hope that your preparation with this series is going well. In case if you have not registered for the Microsoft in 29 days self-paced course, so you can find the course link in the description and you can register yourself for the course. After registering, what you can see is you can click on the start option and then you can see that we have provided the recordings for each and every day along with the problems. Like if I click on day 16, so you will be able to find the two recordings of the problems, like two problems recordings individually that we do. Apart from this, you'll get access to the all five problems that we give. Like two problems we solve in the batch and other three problems we give as homework. Other than this, you will also get access to the leaderboard where you can check that where you are standing amongst your peers. Okay, and you will also get the discuss section, so you can discuss your doubts with your peers. Now let us discuss this problem, that is height of a binary tree. So the problem says that we'll be given a binary tree and we have to find its height. So what do we mean by the height of a binary tree? Suppose that we have been given the binary tree as 1, 2 and 3. So in this case, they are saying that the height of this particular binary tree is 2 because this is height 1, this is height 2. So basically height is the depth of the binary tree. Okay. Suppose if a binary tree, let's take the second example. So suppose if the binary tree was given as 2, 1 and 3. Okay, suppose this kind of a binary tree was given. So this binary tree height is 3 because total 3 levels are there. So how can we find it? So one of the ways of doing this could be a level order traversal. Okay, what we can do is we can simply do a level order traversal and one by one we can keep on incrementing our level. Like this will be height 1, this will be height 2 and so on. Suppose if this type of a tree has been given to us, so in that case this will be level number 4 and that will be the height of the binary tree. Okay, so we can do it using the level order traversal as well, but level order traversal is okay, but we can also do it using something that is much more optimal, that is a recursive approach, that is the post order traversal. So what we can do here is if we try and analyze, suppose that we have been given a tree like this. Suppose we have been given 1, 2, then we have been given 3, then we have been given 4, let's say we have been given 5, suppose we were given 6 here, suppose we are given 7, and then we are given 8, and suppose we are given 9 as well. Okay, so what will be the height of this binary tree? The height of this binary tree, that if I observe, it's 1, 2, 3, 4 and 5 and 6. Okay, so the height of this particular binary tree is 6. How can I get that? So for this what we can do is, like, you can maybe try to do a brute force approach, but in optimal manner what we can do is we can apply the post order traversal for this particular thing. What we can do is we can try and first of all find the left height and the right height, then whichever height is the maximum we can take that. So if we do this, so suppose I am standing at this one. So what is the left height? What is the left height? So left height returns me a 1. Okay, the left height is actually 1. And what is the right height? So if I check for the right height, so what will I do? Like if suppose I talk about 3, so what is the left height of 3? The left height of 3 is nothing but 1, 2, 3, 4. 4 nodes are there. So left height is 4 for 3. And what is the right height of 3? 3. So the right height for this node 3 is nothing but 2. So I will do what? Like actually the height of this part is what? Actually the height of right part of 3, like right part of 1. Actually the height of the right subtree of 1 is nothing but 4. Okay, it's 4. So if it is 4, so that means that what we are doing, if you observe, so total 5 nodes are there. Okay, so total number of nodes are what? Like total 1 node, 2, 3, 4 and 5. So height of the right is 5. So will I return a true and get the height as 5? No. Basically what will happen here is, if we will observe this particular diagram, let's say if I draw it in a much simpler manner. Suppose if I draw a 7 here, then I draw a 6 here, and I draw a 9 here. Okay, if this kind of a tree I draw, so one thing that we can easily observe is that for this 3, its left child will return its height 2, and its its right child will return a height of 2. It's for 3, its left child would return a height of 4. Okay, once this part is happening, so what will happen here? If we consider this part, so we can simply say that we'll take the maximum. Okay, what we will do is we will take the maximum of the left height comma the right height plus 1. Why? Because that node will add. Why? Because suppose that if we check for 1, okay, if we start checking for 1, so left height is nothing but 1. Okay, left height is 1. What is the right height? So right height is nothing but 1, 2, 3, 4, 5. So right height is 5, so right returns a 5. So we will take the maximum out of it. Okay, because we want to find the height of the 3, so we'll take the maximum out of the left and the right. So maximum height is 5. plus 1, because this node also, the root node also will include. Okay, so this thing we'll do for all the nodes, and then we will get the answer. How? So suppose if we start from this particular root node, so first of all we'll go to the left. So for this 2, its left is 0, right is 0, so that means it will return what? Maximum of 0 comma 0 plus 1, so it will return a 1. Okay, then I come to this 3. When I come to this 3, so first of all I'll call for the left child. It goes to the left, it goes to the left, and it goes to the left. So for 6, its left child is returning a 0, its right child is returning a 1. So that means that you will take the right, because right is the maximum, because what you will take is, you will take the maximum of the left height comma the right height plus 1. Okay, so this is nothing but post order traversal. First of all you are finding the left height, then the right height plus 1. Okay, so what we will be doing here is, we will simply say that we'll return this thing. Okay, so what we will be returning is, we'll be simply returning from 6, will return nothing but 1 plus the right height, because right height is maximum, so 6 will return a true. For 7, we can say that its left height is 2, and the right height is what? The right subtree height is nothing but 0. So we'll take the maximum for 7. So for 7, the maximum will be maximum of the left and the right height would be 2. So because left is maximum, so 2 plus the node 7 will also be added, so we'll add one more, so that means we will return 3. So that means that for 7 will return a 3, because actually for the rooted at 3, the maximum height is nothing but 3. Rooted at 7, the maximum height is 3. Okay, then for 4, the right height is actually 0, left height is 3, so we'll take the maximum out of 0 and 3. So that means for 4 we'll actually be returning 4 here, because we'll add this particular node as well. Okay, so the 3 plus 1, so height will be 4. Now if we check for the right of 3, this node 3, so for 3 its left is returning a 4, but for 3 its right side is returning what? Its right side would return a 0, because for 6 the value will be returned as 1, and for 5 the right child will return a 0, and for 5 the left child will return a 1, so you include 5 as well. So maximum of left is left comma right is 1, 1 plus 1 is 2, so that means 2 is the thing that you will return. So for 3 you are getting the left subtree height is 4 and the right subtree height is 2. So what we will do is, we will return the maximum of the 2, so maximum is 4. Now 4 plus 1, because you will include this particular node as well, so 4 plus 1 would be nothing but 5, so we'll return a 5 here. Now when we consider our parent node, that was 1, so for 1 we return our left child. For 1 the left child is returning a height of 1, the right child is returning a height of 5, so we will do what? We'll take the maximum out of the 2, so maximum is nothing but 5, plus adding that current node value, so current node, not the value, current node, so because the height will increase, so that means the height would be 6 here, and that is the height that we can see, because 1 level, 2 level, 3, 4, 5 and 6, so 6 levels are there, so we are returning the height as 6. This is what we are doing using recursion, and if we do it this way, so the time taken will be nothing but like we are traversing all the nodes. Okay, so for this particular approach, the time taken will be order of n in the worst case if it is a skewed tree. So let us try and write the code for this particular approach. So what we will be doing is, we will say that if it happens that suppose the root that the current node that we are at, okay, if suppose that the current node that we are at, if it is equal to null, okay, so that means if the current node is null, so we will simply return a 0, because actually there will be no height of that contributed by the node, because it is null. Otherwise what we will do is, we will do a post order traversal. So first of all we will find the left height, so the left height will be what? The left height, or we can say L, will be nothing but, we'll call the height function recursively, and we'll pass the nodes left part. Okay, we'll pass the left of the node. Okay, then what will be the right height? Okay, so L is equal to, L will tell me that okay, this is the left subtree height. Then R will tell me what? R will tell me the right subtree height, so it will be nothing but height of node right. Okay, that will be the thing. Now what will I return from this particular call, from a particular call? So what will I do? We will simply return what? We'll return the maximum of the left subtree height comma the right subtree height plus 1, because I'll include the node. That is how I'll get the height as we discussed. Let us try and compile this code as well. So it seems to work on the samples. Let us submit this code. So you can see that our problem was able to pass all the test cases. Now talking about the time complexity of this particular approach. So time complexity in the worst case would be order of n. Why? Because if suppose that the tree is kind of skewed, if it is just one direction, all the nodes, like 5 nodes suppose are there and all of them are in one direction, so in that case this will be the part. And since we are using recursion, so the stack space that would be taken would be order of n in the worst case if this kind of a skewed tree is given to us. Thank you for watching this video. In this video we will discuss the problem maximum path sum between two leaf nodes. So the problem says that will be given a binary tree in which each node element contains a number and the maximum path sum from one leaf to another node is what we have to find. So we'll be given a binary tree in which every node will be consisting of some values, and what we have to do is we have to simply return the maximum path sum that is possible from one leaf node of the tree to another leaf node of a tree. So suppose if we have a binary tree like this, okay? So if you have a binary tree like this, so this is a leaf node, this is a leaf node. Basically in a binary tree, what is a leaf node? A leaf node is nothing but a node which does not have any child. Now in this case we can observe that the path would be this, okay? Suppose if I draw a bigger tree, and let's take the example then. So if we draw the tree like this, then in this case what will happen? One of the paths from the leaf node to the another leaf node would be this, and another path that I could take is from this to this, right? And another path from the root to leaf could be this particular path, one could be this, and another could be this. So there could be these paths possible, right? Suppose if I draw a bigger tree, suppose I draw a tree like this, okay? In this case what will happen? This would be one of the paths, okay? Then this would be another path. Then what will happen? These are the two paths that we have discussed. Then another part could be this, another part could be this, another part could be between this node and this node, like this path as we already discussed. Then another part could be this particular path, okay? Then there are several other paths, like we can say that this particular path is also possible and this particular path is also possible, right? So there can be various possible paths. So what we have to do in this problem is we have to return the maximum sum path from one leaf to another leaf. So let us take this example for our test case and see what happens. If we have this particular example given to us here, so what we'll be doing here is, if we have 3, then we have 4, then we have 5, then we have minus 10, and we have been given as some value as 5, okay? So what we can observe here is that we can get the values, right? So the maximum path here would be nothing but this particular path. Let's say if this was 4, right, this is actually 4. So the maximum path that we can see here is this particular path from one leaf to another leaf. This particular path is the maximum path. So how can we get that? So for getting this, what we can try and do is we can try and do the post order traversal, okay? We can basically do the post order traversal. First of all, we can get some data. Suppose if the current node is not a leaf node, then we can get the data from its left subtree and from its right subtree, because for this 3, what is the maximum path in its left subtree? So the maximum path is nothing but this 4 and 4, this path. And what is the maximum path in the right subtree? This particular path. So we'll take this up, and the overall sum will be nothing but the left subtree sum, which will be 8, the right subtree sum, which will be 5, plus the current node value, okay? That is what we will try to do. So what we can do here is we can try and do this post order traversal. But first of all, if suppose that I call a recursive function, okay, initially we can mark our answer or our sum as nothing but int maximum, okay? Initially we can mark our answer as int minimum, sorry, because we'll try to mark it as minimum possible, like negative infinity. Then what we will do is, suppose if the root is null, right? Suppose I have called a recursive function, and if the root is null, suppose if root is actually null. So if the root is actually null, in that case we will simply say that we can simply return 0. Otherwise, suppose that if the root is a leaf node, so when will the root be a leaf node? So if suppose that the root's left is not equal to null and the root's right is not equal to null, okay, in that case what will you do? In that case you will simply return the root data, okay? How? So in that case we will simply return this minus 10 from here, okay, and we'll simply return 4 from here to this particular node. Now when I come to this 4, so I will check, is it a leaf node? No, its left and right both are existing. So if for this 4, if its left child is also existing and its right child is also existing, in that case I will say that I can take out the sum. So what is the sum? Sum is nothing but the left subtree sum, the maximum path sum in the left subtree till the leaf node, and the maximum path sum in the right subtree till the leaf node. So that is nothing but 4 minus 10 plus 4, and the root data, because I'll include the root as well in that particular path. So that would be nothing but minus 2. And is it greater than the int minimum? Yes, it is greater than the current answer, that is int minimum. So I'll update the answer as minus 2, okay? Once I have updated this particular answer, so what we will be doing is, once we have updated this, so we can see that our left subtree is returning a minus 10, our right subtree is returning a 4. So which path will you take? Let's consider for this 3. So for this 3, we want a left subtree to give the maximum possible path till a particular leaf node. So for 3, we want to consider this particular path. So what we can say is that for this particular node, its left subtree is returning a -10, right is returning a 4. So if we see that, so according to this, what we will do is, if we can say that we will return maximum of the left subtree comma right subtree plus the root data. That is nothing but 4 is like among -10 and 4, the right subtree is returning maximum, that is nothing but 4, plus the root data is actually 4, so we'll return what, the right subtree data, that is maximum. So for amongst left subtree and right subtree, that will be 4 plus 4, that would be 8, because I'll be taking this particular path in the left subtree. Okay, that is what I will do. Okay, so that is what I will return. But suppose that if it happens that this is when the current root node is not a leaf node. But suppose if this kind of a situation is there, okay, suppose if this kind of a situation is there, so if there is this node whose left subtree does not exist, so in that case, what will I return? I'll simply return nothing but the right subtree data plus the right subtree, that is nothing but the maximum path in the right subtree till the root node plus the root data. Okay, and there could be another circumstance, that suppose if we talk about a tree like this, okay, and suppose if we are at this node currently, if we are currently at this blue node, then what can happen is, for this particular node, its right is not existing. So in that case, what we will return is, we will simply return the left subtree plus the root data. So that is how, using the post order approach, we can try and solve this particular problem. Let us quickly check out the code for this particular problem. Before that, one more thing, that since the time complexity, what will be the time complexity for this particular approach? So the time taken for this particular approach would be nothing but order of n. Why? Because we are traversing each node exactly once, and the space complexity will be, if we consider the recursive stack space, then it will be order of n. If we don't consider it, then you can say it as order of 1. Now let us quickly check out the code that I have written for this particular problem. So what we will be having is, we'll be having the result initially as int min, then we'll call this particular function, and suppose that if the root is equal to null, in that case we will simply return 0. Otherwise, if the left child is null, if the roots left is equal to null, okay, and the roots right is equal to null, okay, in that case, what I will do is, in that case, I will simply say that if the roots left is null and the right child is also null, so we'll simply return the root data, because that means that the current root is a leaf node. Otherwise, what we'll do is, we'll calculate the maximum path sum in the left subtree till a particular leaf, and we'll calculate the maximum path sum in the right subtree till a particular leaf. And if it happens that the current node that I am at, if it is not a leaf node, then I'll check that whether this particular current sum, that is the left subtree sum plus the right subtree sum plus the root data, if it is greater than the current result, so I'll update it, and then what I will do is, I'll simply return the maximum of the left subtree comma right subtree plus the root data. And I will also check that, suppose if it happens that the left if the left child is null, okay, if the left child is null, so in that case, what we will do, if the left is equal to null, okay, suppose that if the roots left is equal to null, okay, so in that case, what we will do, if the roots left is null, then we will simply say that we will return what, we will simply return this thing, that is nothing but, we will simply return the root right subtree plus the root data. Otherwise, what we will do is, if the right subtree is null, then we will return nothing but the left subtree plus the root data. Now let me try and compile this code to see if it works on the samples or not. So let us compile it. So it works. Okay, it says that return, some issue is there. Let's just check, is there some issue? Let us just compile quickly. I expected node star. Okay, we are getting a bit of error here. Let us quickly check that up. So in this case, like, we can say that, suppose that if the root, okay, one bracket was extra, sorry, in this part, we can now run it, compile it. Now it should work on the samples as well. Okay, it says that expected colon, are we missing some colon? Yes, we are missing this colon here. Now it will work, we were missing the colon. Okay, works on the samples. Let us submit this to see if it gets accepted or not. So you can see that our solution was able to pass all the test cases. Thank you for watching this video.